Hello everyone! Today I'm going to present an overview of our paper Online Hierarchical Partitioning of the Output Space in Extreme Multi-Label Data Streams. This paper was just accepted at ECAI, the European Conference on Artificial Intelligence, and I'll begin with the motivation, the problem, then I'll present the iHOMER framework, presenting its results, sharing the conclusions and future work. Nowadays, there's a lot of data being generated all around us, from sensors, transactions, social media, and this presents both opportunities and challenges, as it requires advanced techniques to deal with this large amount of data, extract meaningful insights, and support informed decision-making. Traditional machine learning approaches, what they do is that first we gather the data, then we process it, train a model, and finally deploy a solution. And this works well when data is already known in advance and data distribution doesn't change, but it has limitations. Because in real-world scenarios, there's concept drift, and the patterns in the data change due to direct changes in the features or changes that affect the decision boundaries of the models that were previously trained, and so they become less accurate or even obsolete. So in data stream mining, in online settings, what we do is that instead of waiting for large data sets to accumulate, we analyze and process data continuously in real time, adapting to changes as they occur. Indeed, in real-world applications like recommendation systems or healthcare, it often involves dealing with this data arriving associated with multiple labels. For example, imagine a personalized health monitoring system. Each time new biometric data is collected, let's say heart rate, blood pressure, glucose levels, the system needs to assign labels. For example, if the person requires insulin, yes or no, the risk of hypertension from 1 to 5. And these conditions of the patient are evolving over time, and there are several challenges that current traditional models cannot fully address. I would like to start by aligning a difference between changes and concept drift. In concept drift, the underlying data distribution changes over time, specifically in the conditional probability that affects the predictive model. So beyond changes in the features or in the decision boundaries, these changes in the label space, for example, the label cardinality, how many labels we have per instance, may induce concept drift if they reflect a shift in the conditional distribution, leading to performance degradation, so the model becomes less accurate. And here, one problem is to avoid, the problem is that we should really avoid catastrophic forgetting, which is, even though we want to learn with new data, we should also keep the memory of the past distributions and what it previously learned. So we need to find a balance between plasticity and stability. We want our models to adapt, but keeping the memory from the past. And traditional multi-label models often assume that the relationships between labels are fixed over time. But in real world, these dependencies evolve, let's say because of user behavior, new trends, and there are so many different types of changes that models usually only detect one of them or one specific type of concept drift, lacking an overall drift detection approach. For example, here we see that some labels appear, others disappear. Thirdly, labels are rarely independent, and presence or absence of only one label really influences the others. So capturing all of these dependencies is crucial, and models that capture and treat each label separately, for example, binary relevance, ignore these dependencies. So they are missing valuable contextual information. And lastly, in extreme multi-level settings, the number of possible labels is so large, let's say hundreds or thousands, that these models that treat all of them at the same time become very computational expensive as the number of labels grows. So we should find a way to create a new algorithm that is under these constraints. So this is really the research question. How can we develop a new online multi-label classifier that effectively adapts to evolving output dependencies and concept drift in extreme multi-label data streams while maintaining efficiency under resource constraints? Let me briefly go over some key related work. Multi-label models can be categorized along 4 dimensions. For example, one is dataset space. Models can focus on different spaces to capture their structure. So it can be their feature space using the attributes to model all of the dependencies. For example, that's what happens in decision trees. Instance space, leveraging the similarity between instances, for example, KNN or other clustering techniques. Or label space, modeling the structure among labels and their hierarchy. Secondly, regarding dependencies, we have conditional dependencies that consider the relations between labels given the input features, or unconditional dependencies that model label co-occurrences without conditioning on input features. This is simpler and faster, but naturally it lacks some context. Thirdly, regarding the order of the correlations, we have first order correlations that assumes that there are no label correlations. Secondly, we have second order that captures pairwise label relationships, and high order, where models capture the full dependencies in the label set. And lastly, regarding instance location, models can be either global or local. Global models assume label correlations are consistent across the whole dataset, while local models tailor these correlations to each instance or region, ignoring the overall dependencies. And most hybrid and global models assume that there's a static situation in patterns in the data, lacking adaptability. And few approaches handle all of these, being able to deal with concept drift, as I just referred. So, yes, we are presenting iHOMER, incremental hierarchy of multi-label classifiers. So, we see that there are 2 main models being trained over time. We have the main learner and alternate learner. And we see that there's a hierarchy in the labels, and when there is concept drift and it is verified and confirmed statistically, we replace the main model by the alternate model. And these figures suggest that there's a hierarchy that was very complex, it was being learned over time, but it was replaced by a simpler one, suggesting that all of the things that were learned before are no longer relevant, so we should find a new way to model that, like a reset, for example, but it's just a replacement by the alternate model. And also, we see, for example, in the first hierarchy, that we have 5 labels, and we have 3 clusters that model labels separately. So they are disjoint clusters, and each label is only present in one cluster. For prediction, and to get the prediction for a new instance, what we do is that we combine the predictions by all of the clusters, and that's what the orange line represents. So now we need to solve a question. We need to learn how do we build these hierarchies that are like the foundation of iHOMER. For this, let's imagine this situation where we have an instance, a figure with 5 labels. And what we'll do is that for each pair of labels, for example, mountain and beach, we'll compute the ratio between the number of shared labels and the number of total unique labels. And this ratio is known as the Jacquard index. With these measures, we'll build a label dissimilarity matrix, not a similarity matrix, because Most clustering algorithms are based on distance metrics, not similarity metrics, and expect low values. So, as we are going to see just right after this slide, we need to have these measures serving as input to a clustering algorithm. So we'll use not Jaccard index, this ratio, but 1 minus Jaccard index. And the similarity matrix that we'll build can look just like this one. We have 5 labels and we have the values for each possible pair. And given these values, as I just said, we'll use them as input for an adaptation of an online divisive agglomerative clustering. And I say an adaptation because this technique usually uses Pearson correlation coefficient, but this coefficient assumes that data is real valued and assumes linear relationships between time series, which doesn't really match our case because here what we want to model is a binary presence or absence of labels in a given instance. So that's why we'll use not Jaccard index, but as I just said, 1 minus the Jaccard index. This algorithm already tracks the diameter and distances between clusters and how they change over time to signal concept drift. The opening bound serves as our confidence way to track confidence and as a threshold because it analyzes how many samples we need to be confident that what we are observing is close to the truth until a given time point, given all of the points that it's already seen. So we build this hierarchy. The final clusters are the ones in blue. And we'll train a basic learner for each cluster. Here we have another trick. Because in real-world data streams, we know that for many instances, we do not have only one label. So for each instance, we have many labels. And we see that in many scenarios, we have clusters of only one label, but it doesn't really make sense to be predicting only one when we know that they do not appear alone. So what we do is that we use a majority label set classifier to analyze the majority the most common label set size. So what is the number of labels that are most commonly predicted together, at least? And given this information and many rules that we defined, we cluster these labels together because even though we have a really good hierarchical structure, we don't really want that level of specificity. So we create rules taking into account the depth, the relationships of the leaf nodes. And as we can see here, the splits are not only one by one, but we have many different splits, and we have data sets with really different cardinalities, densities, number of labels directly. So yes. This figure illustrates how these hierarchies evolves over time in summary. So we have the hierarchy, it evolves, some labels disappear, some other might appear, and now let's focus on the base learner, because the base learner, as I said previously, is represented here by this large blue circle. And each classifier works as a multi-label ensemble composed of several single label classifiers, because MLHAT, which is a very complex algorithm publicly available from a Spanish colleague that just finished their PhD, is really efficient, and it works like an ensemble that at the leaf level, it works as single label classifiers. Indeed, MLHAT trees evolve over time, starting with a single node that splits as more instances from the stream arrive. And the model creates decision trees where each internal node tests a feature, and each leaf as its own multi-label classifier. All of these adapts, the leaf classifiers become more complex, become better predicting label sets, and it detects when the data distribution change because it creates background trees that test new possible splits, and if the new splits perform better, then it replaces the old branches with the new ones. Regarding the methodology of iHOMER, we evaluated it on 23 real-world datasets and compared it to 19 multi-label algorithms, 5 global, 14 local, and we evaluated and tracked several measures, and we tracked also several of them over time. These datasets, they differ in cardinality, density, and mean imbalance ratio, meaning that overall the number of labels per instance really varies and we have many different scenarios to compare. Regarding our results, what we did is that for each measure, for each dataset, and for each algorithm, we looked at all of the results individually. We also analyzed the averages performances across datasets and across algorithms. We analyzed these qualitative regarding the visualizations of metrics over time. We did the Friedman test to assess if there are indeed statistical differences in performance. And as our results said, yes, there are statistical differences. We performed the NAMI test for a 90% level confidence, and we used it to plot on the critical differences diagrams in the next slide. Lastly, we also really wanted to know if iHOMER, building this disjoint set of clusters and training MLHAT on each of them, is really better than MLHAT by itself. And yes, results show that iHOMER is 10% better, and all of these results are statistically significant. Other metrics also show improvement. However, regarding macro F1, the results are worse. And this might be because iHOMER builds, as I just said, disjoint clusters, and this causes that small or rare labels that should be grouped with fewer samples have limited learning. So as they are not really well covered, this really makes it worse. But a way to improve this in the future is to, for example, introduce label aware rates that give more importance to rare labels during training, or allow some overlap in the label clusters, such that these rare labels can appear in multiple groups and benefit from a shared learning. This plot illustrates how iHOMER in the orange dot performs regarding all of the other baseline methods, and we see that results are really satisfactory. This slide illustrates the critical differences diagrams, where iHOMER consistently ranks in the top 3 in terms of performance. And regarding this visualization of both sample accuracy on top and subset accuracy in the bottom, we see that iHOMER is more stable, does not have so many sharp variations. For example, MLHAT, it has sharper variations, and if we compare it also to random clusters that where each MLHAT is trained, the yellow line, we see that it really fails to respond to changes. It doesn't really have much adaptability. So iHOMER really stands out as a really great alternative. As a future work, we would like to see how iHOMER behaves in datasets where there are explicit location of concept drift, where we can really see how it adapts. But it's still iHOMER the first approach to introduce hierarchical label space partitioning in online multi-label settings. And we also would like to evaluate how all of these changes occur, making it more transparent and explainable. And we would also like to make a better assessment in terms of computational costs and efficiency, even if we do some better hyperparameter tuning to coordinate all of these changes over time. So thank you so much. I hope this overview was helpful, and see you in the next video.